You've probably never stood next to a nuclear submarine, but imagine you did. You're on a dock somewhere on the American coastline, and in front of you is a black steel shape so large it barely looks real. 140 meters long, 10 meters wide, no windows, no exhaust, no visible propulsion system, just a hull, a sail rising from the middle, and absolute silence. It doesn't look like a weapon. It doesn't look like a power plant. It doesn't look like an apartment building. But it is all three, running simultaneously, right now, somewhere under the ocean. Most people know nuclear submarines exist. Almost nobody knows how they actually work. Not the vague answer you got in school. The real answer. How splitting atoms moves 10,000 tons of steel silently through the ocean at 46 kilometers per hour. How the same physical process that could level a city gets tamed into a closed loop that boils water, spins turbines, and drives propellers through black water at 240 meters depth. How a crew of 135 men lives, eats, sleeps, and launches cruise missiles without surfacing for months at a time. That's exactly what we're getting into. The submarine in question is the Virginia class, built by the United States Navy, commissioned at a cost of around $2.5 billion, worth closer to $4 billion in today's money. For context, its predecessor, the Seawolf, would cost roughly $9 billion adjusted for inflation. The Virginia class was the more affordable answer to the same problem, and 66 were originally planned. Only 22 were completed. What you get for that price is something that defies easy categorization. At a 140 meters long, it stretches nearly the length of 4 basketball courts, laid end to end. Its beam measures 10 meters across. If you hollowed it out and started stacking school buses inside, you could fit 80 before running out of room. Internally, the submarine divides into 5 distinct sections. The nose carries the sonar arrays and missile tubes. Behind that rises the sail, housing navigation and communications equipment. Below it sits the control room. Further back is the crew living space, then comes the nuclear reactor and engine room. And at the tail, the turbines, gears, and propellers that actually push this machine through the water. 3 identities packed into one hull: a precision weapons platform, a self-contained nuclear power station, a pressurized habitat where human beings live for months without seeing daylight. Before any of that makes sense, you need to understand how the submarine finds its targets. Everything the Virginia class knows about the world outside its hull comes through sound. Not cameras, not radar, sound. Because radar does not work underwater, and light disappears within a few dozen meters of the surface. Sound, however, travels through seawater remarkably well, and the Virginia class is built around that fact. At the very nose sits the conformal large aperture sonar array, operating in 2 distinct modes. Active sonar sends out pulses that travel through the water, strike an object, and bounce back. The computers measure the return time, apply the known speed of sound in seawater, and calculate the exact distance to whatever that object is. Fast, precise, effective. But active sonar has a critical problem. The moment you ping, everyone in the water knows exactly where you are. So the Virginia class relies primarily on passive sonar, which emits nothing at all. It simply listens, continuously, mapping ocean floors, detecting minefields, tracking other vessels by the sounds their machinery produces. Additional arrays run along each side of the hull. A long towed array trails behind, silent, invisible, and fully aware. Just behind the sonar section sit the Virginia payload tubes loaded with Tomahawk cruise missiles. Launching one from underwater is not a simple process. The submarine ascends to its assigned depth. The hatch opens. High-pressure compressed air ejects the missile upward through the water column. The tip breaks the surface. The rocket booster ignites and pushes the missile clear of the water. The booster falls away. The main engine engages, the wings unfold, and a cruise missile that was sitting in a pressurized tube is now flying toward a target hundreds of kilometers away. The whole sequence takes seconds. The torpedo room handles close engagement differently. The Mark 48 torpedo drives to 32 knots on a piston engine, trails a guidance wire back to the submarine for real-time navigation updates, carries a warhead equivalent to over 500 kilograms of TNT, and reaches out to 12 kilometers. If it misses, it does not keep going. It circles back, activates its own onboard sonar, and starts hunting. One submarine, sitting silently in dark water, can simultaneously reach targets in the air, on the surface, and beneath it. Rising from the top of the hull is the sail, the submarine's entire connection to the world above the surface. The navigation bridge sits at the very top, an open platform where commanders can observe when the boat runs on the surface. Below that, two photonics masts extend and retract electronically. These are the modern replacement for the periscope, capturing high-resolution imagery and feeding it directly to screens in the control room below. Behind them sits the snorkel mast, allowing backup diesel systems to draw air from above without fully exposing the boat. Above all of it, the satellite antenna maintains a military-grade encrypted data link to the outside world. Drop down from the sail and you are in the control room, the operational brain of the entire vessel. The sonar section dominates it, staffed by more technicians than any other station, because sound is everything down here. The photonics and navigation department links directly to the masts above. The radio room handles all incoming and outgoing communications. Combat control at the back is where missiles and torpedoes are actually fired. Further back is where the crew lives, and this is where the human reality of submarine service becomes difficult to fully absorb. 119 permanent bunks, a galley, a wardroom where sailors eat and officers conduct mission briefings. No windows anywhere, no natural light, no fresh air that hasn't been mechanically processed. The ocean outside the hull sits between 2 and 4 degrees Celsius and is completely dark. Inside, the crew runs rotating shifts, maintains complex machinery, sleeps in narrow bunks stacked 3 high, and does all of this for months without surfacing. It is not comfortable. It is not supposed to be. It is engineered for endurance. And everything those crew members operate draws from a single power source buried in the section directly behind them. Here is the question nobody actually answers properly. How does splitting an atom inside a steel pressure vessel buried in a submarine translate into a propeller turning at the back of it? The answer runs through one of the most elegant engineering loops ever designed. The reactor core contains uranium fuel rods. When a neutron strikes a uranium-235 atom, the atom splits, releasing heat and 2 or 3 additional neutrons. Those neutrons strike other uranium atoms. Those atoms split. More neutrons release, more atoms split. This is the chain reaction. And left uncontrolled, it accelerates towards something catastrophic. So between the fuel assemblies sit control rods made of neutron-absorbing material. Lower them deeper and they slow the reaction. Raise them and it accelerates. Lower all of them completely and it stops entirely. The heat produced heats water in the primary loop, kept under around 155 atmospheres of pressure so that even at 320 degrees Celsius it stays liquid and cannot boil. That superheated pressurized water circulates through a steam generator, transferring its heat to a completely separate secondary loop through metal walls only. The radioactive primary water never mixes with the secondary water. The secondary water boils, converts to high-pressure steam, strikes turbine blades with enormous force, spins the turbines at high speed. The turbines connect to reduction gears. The gears turn the propeller shaft. The shaft turns. The submarine moves. The steam then passes through a condenser, converts back to liquid water, gets pumped back into the steam generator, and the cycle repeats continuously, feeding itself, wasting almost nothing. The result is a submarine carrying approximately 20 years of fuel in its reactor core. It does not stop to refuel. The only limit on how long it stays submerged is how much food the crew can carry. That same reactor runs every electrical system aboard. The sonar arrays, the combat controls, the air processing systems, the crew quarters. One closed loop, one power source. Running variations of this same design since the USS Nautilus first went to sea in 1955. Moving the submarine forward is one engineering problem. Moving it up, down, and at precise controlled angles through three-dimensional dark water is an entirely different one. The solution the Virginia-class uses is closer to aviation than to conventional seamanship. Ballast tanks sit at the front, middle, and rear of the hull. Each has flood ports at the bottom and air valves at the top. To dive, the flood ports open. Seawater rushes in. Overall weight increases beyond what buoyancy can hold, and the submarine descends. To surface, high-pressure compressed air forces the seawater back out. The tanks fill with air. The vessel becomes lighter. Buoyancy takes over, and the hull rises. It is the same upward force exerted by displaced water that keeps any floating object on the surface, except here, that force is being deliberately switched on and off. Ballast handles the broad vertical movement. Precise depth control and angle management come from dive planes, retractable surfaces near the nose and fixed surfaces at the stern that work almost exactly like aircraft elevators. Angle them down and the nose drops deeper. Angle them up and it rises. Left and right movement comes from the rudder at the stern. In practice, piloting a Virginia-class submarine is genuinely closer to flying than to driving a ship. The crew thinks in terms of pitch, depth, heading, and angle of attack simultaneously, and every adjustment in one axis affects the others. Through all of this, the Virginia-class remains nearly acoustically invisible. The hull shape minimizes noise. Internal machinery sits on dampened platforms that absorb vibration before it can radiate through the hull into the surrounding water. No cavitation signature at operational speeds. No surface wake. No radar reflection. A vessel the size of a city block, carrying a nuclear reactor and enough firepower to conduct a sustained air campaign, moving at combat speed and producing almost no detectable signal at all. What looked like a black steel cylinder on a dock turns out to be something considerably harder to categorize. A self-sustaining underwater civilization powered by controlled atomic fission. A weapons platform that can reach targets on land, on the surface, and beneath the water simultaneously. A habitat where human beings live and function for months without sunlight, fresh air, or contact with the world above. And an engineering achievement that runs on 20 years of fuel, while leaving almost no trace of its existence in the water around it. The Virginia-class does not need to refuel. It does not need to surface. It carries its own power plant, its own weapons, its own world. The next time you hear the words nuclear submarine, you will not picture a vague, dark shape sliding beneath cold water. You will know exactly what is inside it, how the reactor loop works, how the ballast tanks breathe, how a missile travels from a pressurized tube to open sky in seconds. And you will understand why it remains, by almost any measure, the most complex and capable machine that human engineering has ever put beneath the sea.